For our experiment, we are going to use bromothymol blue to indicate the pH of solutions that include various concentrations of hydrochloric acid, sodium hydroxide, potassium dihydrogen phosphate, and dipotassium hydrogen phosphate. Bromothymol blue is a pH indicator that is used to distinguish between weak acids and weak bases, indicating pHs between 6.0 and 7.6. As seen by the name, the substance itself is blue, but in a neutral solution it will turn green. In an acidic solution it will turn yellow, and in a basic solution it will be blue. Hydrochloric acid, also referred to as HCl, is an acid with a pH of about 1 to 2. It is the aqueous solution of hydrogen chloride gas and is found in gastric acid in the human stomach and is also used in the production of gelatin. Sodium hydroxide, also known as NaOH, is a base with pH of about 12. Other names of sodium hydroxide include lye and caustic soda. NaOH is commonly used in many worldwide industries such as the manufacturing of pulp and paper, textiles, drinking water, soaps, detergents, and as drain cleaners. Potassium dihydrogen phosphate, also known as monopotassium phosphate, and dipotassium hydrogen phosphate are both buffers. A buffer is something that, when added to a solution, will resist the change of pH. In this experiment, you will see how effective buffers can be. First, you will need 375 milliliters of distilled water, 15 milliliters of 1 molar hydrochloric acid, 15 milliliters of 1 molar sodium hydroxide, 1 milliliter of bromothymol blue indicator solution, 2 grams of potassium dihydrogen phosphate, 2 grams of dipotassium hydrogen phosphate, 3 150 milliliter beakers, 3 stirring rods, 2 25 milliliter graduated cylinders, 3 droppers, and chemistry goggles. Disclaimer: always wear goggles to protect your eyes during dangerous chemical experiments. Make sure everything is labeled clearly and that you can distinguish between beakers and graduated cylinders. Let's begin. Start by pouring 125 milliliters of distilled water into each of the 3 150 milliliter beakers, as seen in the video. Place a stirring rod in each of the beakers. Use a dropper to place 5 drops of bromothymol blue into each of the 3 beakers. Stir the first solution and use a second dropper to add 1 molar hydrochloric acid until the solution turns yellow. Be sure to add it carefully, drop by drop. You should only need to add a few drops and make sure to record the number of drops it takes to turn the solution yellow. Then, add 1 molar sodium hydroxide into the first beaker, using the third dropper, again, drop by drop. Add as many as it takes until the solution turns blue. This color change should occur only after a few drops. Again, make sure to record the number of drops it takes to turn the solution blue. Set aside the first beaker. Take the remaining 2 beakers that only contain distilled water and bromothymol blue and add 1 gram of potassium dihydrogen phosphate and 1 gram of dipotassium hydrogen phosphate into each of the beakers. Stir until the solids have completely dissolved into the solution. Add 1 molar hydrochloric acid drop by drop until twice as many drops have been added as required to change the color of the solution in the first beaker. While stirring the solution, slowly pour 1 molar hydrochloric acid into the beaker until the solution changes to yellow. Now, let's focus on the third beaker. Slowly add 15 milliliters of 1 molar sodium hydroxide while stirring the solution until it turns blue. Let's take a closer look at the experiment now. The first beaker was originally a teal-greenish color, which indicated that solution is at a neutral pH of around 7. When we first added hydrochloric acid, the solution turned a yellowish color, meaning that the pH was lower than 7, thus indicating that hydrochloric acid is in fact acidic. Note that this color change occurred when only about 15 drops of hydrochloric acid, meaning that only a small amount of the acid is needed for the reaction to occur. We then added some sodium hydroxide, and in about 19 drops, the color of the solution changed from yellow to blue, showing that sodium hydroxide is indeed a base. This also indicated that a small amount of the base is needed for the reaction to occur. After we added the potassium dihydrogen phosphate and dipotassium hydrogen phosphate to the second and third beakers, and then added 3 drops of hydrochloric acid to the second beaker, the solution did not change color. It remained a greenish color, meaning that there was no pH change. However, when we added the rest of the hydrochloric acid to the second beaker, the solution did finally change to a yellowish color. Because the color change did not occur in the second beaker at as many and even double the amount of drops of hydrochloric acid compared to what occurred in the first beaker, that means that potassium dihydrogen phosphate and dipotassium hydrogen phosphate inhibited the color change reaction and pH change to take place. Chemicals that inhibit pH changes to occur are called buffers. Thus, potassium dihydrogen phosphate and dipotassium hydrogen phosphate are buffers. To verify this conclusion, we added the sodium hydroxide slowly to the third beaker, noting that the color change only occurred once all the sodium hydroxide was added to the third beaker. This proves that potassium dihydrogen phosphate and dipotassium hydrogen phosphate are indeed buffers, which prevent the pH from changing when small amounts of another solution are added to the pre-existing solution.